Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to implement a policy gradient solution in TensorFlow for CartPole. We'll be using a linear model for the policy and a neural network for the value function. However, by abstracting out the neural network layers, you can easily test different architectures. If you don't want to code along, although I highly recommend you do, the relevant file in the course repo is pg_tf.py in the subfolder CartPole. So we start out with our usual imports, and next we go to the hidden layer class. This class implements a fully connected neural network layer. The arguments to the constructor are input size, output size, activation function, and whether or not to use a bias term. Inside the constructor, we create TensorFlow variables for each weight and set the activation function. In the forward function, we calculate the output. Next, we have the class policy model. This constructor takes in the input size, output size, and all the hidden layer sizes in a list. The first block of code is building the structure of the neural network. Remember that the final layer uses the softmax function. Next, we create placeholders for the input states, which I've called x, the actions, and the advantages. X will be an n by n matrix, while both the actions and advantages will just be vectors of size n. Remember that actions are integers, which are meant as indexes to arrays. Next, we calculate the output p of a given s using the forward function from the hidden layers. We also set predictop to be p of a given s, since that's what we want the output of this model to be. Next, we create the cost function. First, only the entries of p of a given s that correspond to actions we actually took matter, so we have to either index p of a given s by the actions, or we can create a one-hot matrix and multiply it. We're doing a sum here, but really this is just a way to get rid of the zeros after multiplying the one-hot matrix. You'll see that there is a more elegant way to do this in Theano. Finally, we log this, since it's the log of pi that appears in the cost function. The last step to creating the cost function is to multiply by the advantages and take the sum. Remember that we have to negate this because this is something we want to maximize, but TensorFlow optimizers only have a minimize function. Finally, we set the train op to be one of TensorFlow's optimizers. You can see here that there are a number of optimizers commented out. You are welcome and encouraged to try different optimizers and different hyperparameters to see if you can obtain better results. Next, we have the set session function, which is just a basic setter. This allows us to use the same session for both the policy model and the value model. Next, we have the partial fit function. First, we convert the states, actions, and advantages to the right-sized arrays before we call train op. Then we call the train op. The predict function calls the predict op, and the sample action function samples from the prediction. Notice that we don't have any need for epsilon greedy here. Next, we have the value model class, which is of course going to be used for approximating the value function. This is going to be much simpler because it uses a squared error rather than the complicated cost function that we have for the policy model. In the constructor, we have pretty much the same steps. Create the layers, create the placeholders for the training data, calculate the output and cost, create the train op, and then create the predict op. So set session, partial fit, and predict are all similar to the policy model. Next, we have two play1 functions. I didn't find good hyperparameters for the TD version, so we'll skip down to the Monte Carlo version since it's a little more complicated due to needing to calculate the returns. As input, it takes in the environment, a policy model, a value model, and gamma. We initialize some variables, and remember we have to keep track of the states, actions, and rewards. This is for two reasons. One, they are inputs into the train function, and two, we need the rewards to later calculate the returns. So next, we enter the game loop. We sample an action from the policy model. We do the action. We set the reward to be very negative if the poll falls down. You may want to modify this if you're using a new version of Gym and your episode caps at 200. Next, we append the state, actions, and rewards to our lists. When we're done this loop, we calculate the returns and the advantages. We need to wait until we have the return to calculate the advantage because the advantage depends on the return. Once we have the returns and the advantages, we can call partial fit on both the policy model and the value model. Finally, we have the main function. We start out by grabbing the environment and the input and output size of the policy model. Notice how we're using a linear policy and a neural network for the value function. Next, we create a variable initializer and a session. We then run init and set the session for both models. The next steps are very similar to previous code, so we don't need to look at those again. Let's run this and see what we get. One thing to make note of is how sensitive this is to our choice of optimizer. I would recommend testing out different optimizers with different hyperparameters to see what kinds of results you can get. This is an unfortunate characteristic of neural networks. When this stuff was invented, AdaGrad didn't even exist. So what if a researcher was just never able to find a good learning rate function and just gave up? It's interesting to think about. Perhaps we have a lot of really great tools at our disposal, but because people just haven't found the right hyperparameters to make them work, those tools might get ignored or discarded.